Okay guys, we're starting. We're going to continue going through the paper. Let me just navigate to where we stopped the last time. And let me first quickly share the link. As usually, this stream is going to be a bit shorter than my usual streams, just because I have a meeting that I can't miss. So just FYI there. Okay. Going through Alti plus paper and detecting hallucinations. Okay, just share the link here on Discord. Guys, join the server if you haven't seen it already. Let me just oh my god, through my brain today. Let's go. Okay guys, turning on the live chat. If you have any questions, let me know. Let's go and wrap up this paper. So we've seen the background behind Alti, however you pronounce it. The idea is to figure out how to measure the dependency of a particular token on a particular output token. And what they ended up doing is just choosing this Manhattan distance between the vector, this output vector, minus the transformed version of xj. So that's kind of the logic there. We don't even need to understand all of the details for now. We just want to kind of roughly understand the high level concept, and if we need to debug it, then we can maybe go into more details. Okay, Alti for the encoder-decoder transformer, or also known as Alti plus. So the attention rollout and Alti methods work for encoder-based transformers. However, in the encoder-decoder transformer, the cross-attention hinders its integration. In this section, we present Alti plus, which is the adaptation of Alti method to the encoder-decoder transformer. Okay, so we decompose the self-attention and cross-attention of a decoder layer into interpretable expressions, equation 6, from which we can get the degree of interaction between input and output token representations. That's the equation 9, so 6 and 9. Okay, so that's this one and then this one. Okay. Consider all of these tokens, the set of vector representations of the target prefix tokens as input of a decoder layer. And this is the layer output, figure 4. Okay. And then they say the layer normalization in the decoder self-attention. Layer normalization in the decoder self-attention is applied over the sum of the multi-head attention output and the residual yt minus 1. The self-attention block can be written as, and you can see the formula here. So basically, some residual connection and then the output of the multi-head attention for the previous tokens, and then pass that through the layer norm to get the output here. Okay. Curious they're not using index for like the layer, the output. This is like YTS from which layer? Okay, this is just, I guess, from generic layer. And then where FTS considers alpha, W for the value, and W for the output. Hey there, what's up, man? Of the decoder self-attention. Okay, analogous to equation 7, we can obtain the transformed vectors. And following equations 8 and 9, we get the decoder self-attention contributions, reflecting the strength of the interaction between the previous tokens and the current token in the decoder. Okay, and then decoder cross-attention. The output of the cross-attention block at time step t can be decomposed as. And so here we see the formula. So we have the multi-head attention that attends to the basically encoder tokens. And then we add on top of that the residual representation of the current token. Let me just think for a second. Okay, where YTFS, the residual connection, is the output of the self-attention block, and E is the encoder outputs. We can obtain the transform vectors of the encoder outputs and the residual connection like this. And then following equation 8, we can compute the Manhattan distance between the transform vectors and YT tilde and get the contributions. So we get the contribution of the encoding vectors, of the encoder vectors from the encoder, and we also get the contributions from the self-attention outputs. Okay. So these are the T tokens up until this particular token, and these are the T tokens that attend to the J tokens of the encoder. J is the source context length. The cross-attention residual contribution to YT tilde reflects the total influence of the self-attention inputs to the decoder layer output. Let me just parse this again. The cross-attention residual contribution reflects the total influence of the self-attention inputs to the decoder layer output. Thus, we can get the full decoder layer contribution matrix like this, figure 5, by substituting the residual contributions with the self-attention contributions. So by substituting the residual contributions with the self-attention contributions and weighing every row of the corresponding value of the residual contribution of each time step. Got it. So basically, as far as I understand, here you care, so for this particular field here, I guess these values here are just how much this token, this token, this token, and these decoder tokens contribute to this particular token. That's kind of how I understand this. And then the same goes here. And they've just color coded here. The red one is for decoder, the green one is for encoder. And these are those contribution matrices, or C. Okay. Let me read this last time once more. By the way, we have a bunch of flights here. There's some military exercises that are happening every September. So hopefully you don't hear the noise. So thus we can get the full decoder layer contribution matrix. So that's this thing here, by substituting the residual contributions with the self-attention contributions and weighing every row by the corresponding value. Okay. Let's continue here. So in order to get input token attributions, we apply the same principle as attention rollout method. As described in this section 2.2, Alti builds a graph where nodes are token representations and edges represent the contributions between tokens in each layer. The amount of information flowing from one node to another in different layers is computed by summing over the different paths connecting both nodes, where each path is a result of the multiplication of every edge in the path. Figures 6 and 7. Okay. So basically, I guess these are just like, yeah, these are the contribution weights. So this is not just like this is not just like attention coefficient, and this is like maybe like a value vector or whatnot, and then you sum them up and you get this value here. It's a bit more complex. So this is basically just some abstract diagram of how these contributions are compounded between encoder and decoder. For the source, and then for, I guess, target. So here is how this particular one contributes to this token, and here is how this particular token me gusta contributes to Y3 tilde. Algorithm 1 shows the process to obtain source sentence tokens relevance for the model prediction. We first, so that's figure 6. So we first update the cross-attention contribution matrices by multiplying each of them with the contributions of the entire encoder to account for all the paths in the encoder and cross-attentions. We then iteratively aggregate edges from paths of the target prefix contributions. Target prefix input attributions are computed by multiplying in each layer. Okay, so again, it's hard to get an intuition for what multiplication here means, but they are roughly counting all of the possible paths from this particular token to here, and just weighing and summing up those weights to get the final contribution from this token to this token. Okay, so then the experimental setup. We analyze input token attributions in both bilingual and multilingual MT models. For the bilingual model, we train a 6-layer transformer for the German-English translation task. We use EuroParl v7 corpus and follow blah 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 data setup. Let me see whether, okay, these are just some links. We use byte pair encoding, BPE, with 10K merge operations. For the multilingual model, we use MTM, a many-to-many multilingual translation model that can translate directly between any pair of 100 languages. We use FAIRSEC implementations and the provided checkpoint for the M2M model. We perform the quantitative analysis in 1,000 sentences of the test set of IWSLT 14 German English. For the analysis in 5.5 section, we use Flores 101, dev test split. Okay, all of those are now familiar names. Like we are also dealing with Flores, and we're dealing with all of these different splits, and these are just some familiar names in the machine translation space. So let's see. What do they do? And by the way, this M2M model is basically just a predecessor to NLLB model from Meta. So in this section, we perform a set of experiments to measure the quality of the obtained contributions and unveil different aspects of bilingual and multilingual models. Information mixing the encoder. Information from the input source tokens gets mixed throughout the encoder. Intermediate layer representations acquire contextual information from other tokens in the sentence due to the self-attention mechanism. These guys analyze for an encoder-based model the contribution of input source tokens to its intermediate layer representations. They conclude that the input source tokens contribute little, around 10% on average, to its corresponding last layer representation encoder output. However, by training a linear classifier and with nearest neighbor lookup based on the cosine distance, they are able to recover input token identity 93% of the times. Okay, by training a linear classifier and with nearest neighbor lookup based on the cosine distance, they are able to recover input token identity. We apply Alti method across the transformer encoder and analyze the input relevance of source tokens to intermediate encoder representations. Figure 9. Okay. Our results in the bilingual and multilingual models show that indeed input tokens highly contribute to their associated layer representations. In the last layer, 41% of the input contribution comes from the input token at the same position. Okay. The multilingual model is able to retain above 47% despite its 12 layers. The curves of both models in figure 9 closely match results obtained by this other work, relying on the mutual information between the input tokens and token representations across layers. So contribution of the source input token to the encoder output representation at the same position. We show mean and standard deviation for each layer. Okay, so you can see here, basically, roughly as we go up the layers, of course, the contribution is smaller and smaller for that particular token, which is interesting. Okay. Where did we stop? I think we were here. So in order to evaluate the quality of the proposed cross-attention contributions, we measure alignment error rate against human annotated alignments. As found out by this work, the penultimate layer of transformers tends to focus on learning the source target alignment of words. Therefore, we analyze the cross-attention contributions extracted from the 5th layer from the bilingual 6th layer model. We use gold alignments from this work containing 508 sentence pairs. For comparison, we compute the AER of the raw attention weights and previous methods based on vector norms. So they just compare against some baselines here. Vector norms compute the Frobenius norm from equation 5. And vector norms plus LM plus res, they take the L2 norm, Frobenius norm from equation 6. So as shown in table 1, our method for estimating layer-wise contributions obtained the lowest error rate, outperforming similar previous methods by at least 2.6 points on average. As can be observed in figure 8 as well, attention weights fail at showing alignments with the end of sentence or start of sentence token, concentrating large attention weights. Our method is able to filter this noise, showing almost no contribution from this token. And then they analyze this phenomenon a bit later. Okay, let's see these tables and figures. Figure 8 and table 1. So here's the attention weight, vector norms, some combination, and then this work. And here, again, different work. So here you can see there is a lot of this weight is on top of the end of sentence token. And then the cross attention contributions of the encoder outputs E and residual. And finally, total decoder layer contributions. Okay, so most of it, did they just kind of collapse this here or what? This looks like this one was just collapsed here. And this is the actual contribution. Still not completely clear how to parse this. So this particular token here, let me just see. If we grab closed, we get what? Here is closed is one token above here. So I guess how we should read this is for closed, that debate on the state of the European Union is closed. So for the closed token, we are looking at how these are contributing. IS. So the biggest contribution for closed comes from this one, or the biggest contribution for this one comes from closed, i.e. the last token. It's a bit confusing, honestly. Okay. And the role of the end of sentence token. It has been hypothesized that attention given to special tokens is used by the model as a no-op. This work analyzed attention weights of the cross attention to source finalizing tokens, final punctuation mark, and end of sentence token, and find the value vectors. Guys, by the way, give me just a second. Let me just turn on the lights here. Okay. So source finalizing tokens like punctuation marks and special tokens, and find the value vectors associated with these tokens to be almost zero norm. Additionally, they find that attention weights to source finalizing tokens tend to increase when predicting tokens that heavily rely on the target prefix, such as postpositions, particles, or closing subwords. So it's almost like a no-op. It's focusing on that because you don't want to pass any information from the source to decoder, because mostly you want to focus on some information in the decoder context. The proposed cross-attention decomposition in 3.1 allows us to analyze both the contributions of source and the residual connection, figure 8b. We measure the Pearson correlation between attention weights to the end of sentence token and contribution of the residual connection in the cross attention. We can see in figure 10 that there is a high correlation in almost every layer, especially in the last layers. So we can see in figure 10 that there is a high correlation in almost every layer, especially in the last layer. This demonstrates that finalizing tokens are used to skip source attention, since the higher their attention scores, the more information is flowing from the decoder in the residual, coming from the target prefix. So the correlation between attention weight values given to the token and the contribution of the residual in the cross attention. So layer, index, correlation. Okay, so then what's the conclusion from this chart? Persons are correlation between attention weight values given to EOS and the contribution of the residual. Okay. So the higher the attention weight to the EOS, the bigger the contribution from the residual in the cross attention, which means information flows from the decoder side. Okay. Analyzing hallucinations. This is going to be a fun part. A common issue of NMT models is hallucinations, which are translations that are disconnected from the source text, despite being fluent in the target language. Hallucinations should be reflected in our method as a drop in the contribution of the source sentence. Thus, in this section, we induce hallucinations and measure the source sentence contribution with Alti+. To induce hallucination, we perturb the target prefix sequence of the bilingual model by adding the unknown token. Then we follow the algorithm proposed by Lee et al. To detect which perturbed translations are hallucinations. They measure a blue score of the generated translation with and without perturbation. They fix a minimum threshold blue score for the original translations, 20, and a maximum score for the perturbed translations. And the model is considered to hallucinate when both translations satisfy the thresholds. Okay, so when the original satisfies the threshold and the perturbed one falls below 30. Analyzing the Alti plus contributions, we can confirm that the bilingual model largely ignores source tokens during hallucinations, as can be seen in figures 11 and 12. Let's see, so this goes from like what, German to English, and here apparently there is no attention coming to German tokens. Original has high source contribution, so basically you can use this type of logic, just analyze the contribution matrices to figure out whether you have hallucinations or not. That would be super powerful. How robust is this? That's, I guess, the next question. multilingual model analysis. We analyze the behavior of the multilingual model in different language pairs of the Flores 101 dataset. We include the analysis high resource languages, English, Spanish, and French, and low resource languages like Zulu and Xhosa. High resource languages have been defined as languages with available bytext data beyond 100 million samples, and low resource languages are those with less than 1 million. Okay. That's a good operational definition. By the way, for the model that we trained a couple of days ago for Hindi and Turkish, we had like 36 million sentences for Turkish, and we had, I think, around 3 million for Hindi, which qualifies them as high resource, even though that's just primary data. We didn't have any mined data inside of it. Okay, so figure 13 shows an Spanish to English example in the multilingual model. So again, figure 13 shows the Spanish to English example. We observe an almost uniform contribution of the language stacks across different outputs. The only drop in its contribution seems to happen when translating proper nouns, Mr. William, or anglicisms like hobby. Let's see that. So let's find Mr. William. Mr. Williams. And what else? Or anglicisms like hobby. Hobby. Okay. Source contribution. I want to thank Mr. Williams for introducing me into his hobby. Source contribution to which particular token? Which is observed for other language pairs too, Appendix C, and repeated across the dataset. We hypothesize that the model doesn't need to rely on the language stack, since these words appear across different languages. Dependencies between generated tokens are also observed. The prediction for relies on thanks, Williams on Mr., and into on introducing. Wait, so dependencies between generated tokens are also observed. The prediction for relies on thanks. Thanks for, I want to thanks for. Okay. The same examples can be found. The prediction for relies on thanks, Williams on Mr. and into on introducing. The same example can be found in Appendix for English to Zulu and Zulu to English. And then figure 14 shows results of the source sentence contribution for English to Zulu, English to Xhosa, English to French, and English pairs. Okay, so how should we parse this? For English to Xhosa, English to Zulu, source contribution has, okay, got it. So this might literally show us which of these are lower resource. So the lower this, the lower the resource of the language probably. We observe similar source contribution patterns between the high resource languages and between those pairs involving a low resource language. However, in the low resource scenario, the source contribution is remarkably lower when translating from English. We hypothesize that when the low resource language is in the target prefix, the model tends to behave similarly to when it hallucinates in figure 12, ignoring the source. But when the high resource language is in the target, it is less likely to lose track of the source and thus less prone to enter hallucination mode. Low resource language sentences in the target site may be seen by the model as target prefix perturbations, although further research is required. Okay. How do they get the actual number? Is that just, I guess, average across tokens or whatnot? Okay. English, I want to thank for introducing me to hobby. So English contributes the most. To what? Wait, this is completely confusing. Isn't this the source? So this is the source sentence in Spanish. And then English Okay. I don't completely understand how this exactly works. I know roughly how they compute it. I'm trying to still understand how they're parsing these diagrams. Let me see. I guess that's the most important bit here. How to understand the diagram parsing. Let's see here. Let's go here. Attention weights. So for example, geschlossen, one would expect to see the most weight on the closed. Damit ist unsere Aussprache über den Stand der Europäischen Union geschlossen. This is the dot. This is geschlossen. This is the union. So we expect to see a strong diagonal signal here, right? Damit ist on is. Geschlossen should be on closed. And it is. Geschlossen is on closed. So basically this one focuses the most on closed. Okay. Yet when looking at their work, most of the contributions come from the residual, meaning most of the information is in the decoder itself. And then all of a sudden they have these diagrams here. Do they just sum up across the rows or what? By that logic, maybe this one should be high. Williams should be maybe high. Yes. Okay, it looks like this is just summation across the rows. So source contribution basically tells us, so this is a contribution of English to English. Wait. Got it. So different contribution. I'm just trying to parse this diagram and figure out what's going on. It definitely looks like they're summing across the rows to get the contributions, which means for English, this is how these other ones contribute. So the one that contributes the most seems to be Espanol, etc., and then, okay, and then for I, the one that contributes the most is English token for some reason. Or am I, let me see, am I counting this right? I is here. Nah, I'm confused, guys. This is just, I don't like the paper. They could have explained this on a single example, like just in a bit more detail, explain the diagram itself. Let's see whether analysis. Let's go through this section once more quickly, and then we can skim through the hallucination papers. I think this is just more of a base for the follow-up paper where they use this Alti plus scores to figure out whether they have hallucinations. That's going to be more practical, of more practical interest. We don't need to understand all of the details in this one for now, but let me just try and understand how to parse the diagrams a bit better. So they perform a set of experiments. Let's see where they mention this figure 8. Okay, they mentioned here and here, section 5.3, and just below the section 5.3. Okay. As can be observed in figure 8, attention weights fail at showing alignments with the EOS token concentrating large attention weights. As can be seen, I guess, here. Our method is able to filter this noise, showing almost no contribution from EOS, as you can see here. So EOS, almost no contribution. How much it contributes to this one, to this one. So this value here tells us how much this token here on the x-axis contributes to the one on the y-axis. So residuals contribute the most to the translation. So how much on the x-axis contributes to the one on the y-axis? So let's see whether that logic makes sense. So how much is contributes to close? Okay, a lot, which makes sense because state of the European Union is, I mean, these preceding tokens should kind of influence. So is closed. I would expect the union to also contribute to close by that logic. Okay, let's go to hallucinations paper. Let's just skim it and understand the rough idea. I don't want to spend too much time on these papers. They are not going to be super useful. Detecting and mitigating hallucinations in machine translation. Model internal workings alone do well. Sentence similarity even better. Interesting title. While the problem of hallucinations in neural machine translations has long been recognized, so far the progress on its alleviation is very little. Indeed, recently turned out that without artificially encouraging models to hallucinate, previously existing methods fall short, and even the standard sequence log probability is more informative. It means that characteristics internal to the model can give much more information than we expect. And before using external models and measures, we first need to ask how far can we go if we use nothing but the translation model itself. We proposed to use a method that evaluates the percentage of the source contribution to a generated translation. Intuitively, hallucinations are translations detached from the source, Hence, they can be identified by low source contribution. This method improves detection accuracy for the most severe hallucinations by a factor of 2 and is able to alleviate hallucinations at test time on par with the previous best approach that relies on external models. Next, if we move away from the internal model characteristics and allow external tools, we show that using sentence similarity from cross-lingual embeddings further improves these results. We release an efficient implementation for the considered methods in Stopes. And we kind of went through some of the notebooks last night, basically. Okay, let's skim through some of the charts. Taxonomy of translation types based on the data set. So translations can be correct, they can be errors. They're not detached from the source, but they are errors nonetheless. So they can be under generation, whatever that means, named entity mistranslation, and other errors. Okay, so like maybe error can be maybe like, I guess, syntactical mostly here. Like if you mistype the named entity or something. And then hallucinations, which are detached. They can be oscillatory when you have repetitions, largely fluent, which can be fully detached or strongly detached. Okay, that's just something that we have to understand how they define those methods, those definitions. Hallucination detection quality methods, they are the oracle, internal, external. So the internal ones are the green ones, including Alti. Fully detached, all hallucinations. Okay. So how should we parse this? It's kind of confusing. They are using color both to present the value. So like the more red it is, the lower, the more green it is, the higher the number. No, that's not true, because 25 here is more green than 90 here. So what does the color represent here? So this is like external method. My God. Okay, we're gonna see it a bit later. Kernel density estimation of distribution of the detection criteria by translation pathology type. Okay, so we have fully detached hallucinations in brown, strongly detached, errors, and correct translations. Previous work, this work, internal, external. So this work, internal, fully detached. So what's on the x-axis, what's on the y-axis? Kernel density estimation of the distribution of the detection criteria by translation pathology type. What? Why does this paper make me feel so dumb? Comet, CHRF, reference-based oracles. See you later. How to parse all of those, I have no idea how. Distribution of translation types when selecting the worst 10% of the data set according to each metric. Okay. So they take the 10 worst percent of the data set according to metrics, and then they plot types of errors they're making, right? So what's the ground truth? In the original dataset, these types were annotated in a multi-label manner. For example, the same translation could be annotated both as oscillatory hallucination and as a named entity error. To assign a single label to each translation, we choose the most severe pathology type, with severity increasing clockwise from correct to fully detached. Clockwise from correct to fully detached. Correct, other errors, named entities, under generation, oscillatory, strongly detached, fully detached. Okay, so fully detached is stronger than strongly detached. Okay, for all combinations of, this looks like Flappy Bird, those like pillars in Flappy Bird. For all combinations of a generation strategy and a re-ranker, heat maps show scores for the final translations. Sampling, default beam search, and then re-ranking. Using Comet, Alti, etc. Lab C. I literally don't know how to parse there. I'm either too tired, or this is just completely out of distribution from my brain, how to parse these plots. Number of hypotheses. Comet scores for each generation method and number of hypotheses for each group of generation strategies. We show the best representative. So average Comet. Since when does Comet go into negativity? I thought it's a Comet being negative. Interesting. Number of hypotheses. The more hypotheses we have with MC, Monte Carlo beam search, the better. Okay, I think this paper is going to be useful just to get into some terminology behind errors that these translation systems make. For hallucinations, all the differences are important except the one between Alti versus Comet QE. For correct translations, the difference between Lab C and Alti is statistically significant. Conclusion. We started this work by asking how far we can go at detecting and mitigating hallucinations if we use nothing but the translation model itself. Turns out we can improve the result of the overall detect then rewrite pipeline by evaluating the percentage of source contribution to generated translation. Translations with low source contributions are likely to be detached from the source, i.e. hallucinations. For detecting the most severe type of hallucinations, this method improves previous results twice. For mitigating hallucinations at test time, it matches the hallucination reduction rate of the previous method based on Comet QE. We believe this can motivate future work on model understanding and help practitioners using nothing but model inner workings can allow mitigating hallucinations for a language pair where models such as Comet QA are not available. Okay. Yeah, it's a cool idea. When allowing external models, we propose to expand the method for handling hallucinations from models specialized for quality estimation to a broader set of objectives. For example, sentence similarity from cross-lingual embeddings. We propose to expand the methods for handling hallucinations from models specialized sentence similarity from cross-lingual embeddings. Apart from showing that, for example, LabC improves previous results significantly, we also find that models so far overlooked in the context of machine translation, such as natural language inference, can be beneficial. We hope future work will build on this idea. Some tables and results. Each row of the data consists of the German source sentence, its reference English translation, it is not always accurate, and 1 to 4 machine translation outputs. The machine translation outputs are presented in a random order to exclude the possibility of bias towards any specific method. For each of the machine translation, you need to assign one of the following labels. Okay, acceptable translation, partial hallucination, full hallucination. Under translation, there is no hallucinations, but a significant part of the source is not translated at all. Okay, so that's under translation. Other, there are no hallucinations or under translations, but there are other translation errors that make the translation unacceptable. Wow, fairly ambiguous, especially a part is unrelated. Most or all of the translation is unrelated. And partial, a part is unrelated. Partial or full, under translation, okay, or other. I would assume if you took a look at confusion matrix for people, probably this one is confused mostly with some of these. Unacceptable. Okay, so this is just error. This is when it's detached from the source. This is when it doesn't complete the translation, and this is okay. Okay, let's go. Let's go to the main paper. Hallucinations in machine translation are cases when the model generates output that is partially or fully unrelated to the source. While generally this phenomenon is not that frequent and has a relatively low impact on corpus level automatic metrics, the impact of hallucinations on user experience can be rather dramatic. For example, if a machine translation system generates the staff were very friendly and helpful in response to an input sentence, for example, about a marvelous view from the window, in future a user is unlikely to trust this system. While the problem of hallucinations is known and important, addressing it is very challenging. Firstly, hallucinations are very rare. This is why previous work mostly resorted to settings where models are encouraged to hallucinate. Hallucinations are hard to identify with automatic metrics. That's the second thing. So rare and hard to identify, which I guess is kind of connected. For the most part, hallucinations were defined as translations with low quality according to some metrics, such as, for example, adjusted blue or CHRF, or translations satisfying some heuristic condition. Overall, it was not clear whether proposed methods indeed detect hallucinations, and if so, whether they did transfer to more natural settings. Recently, when revisiting previous work in relatively clean setting, this work found that existing methods fall short and the standard sequence log probability is the most informative. So how do you use the log probability to figure out whether it's a hallucination? To show this, the authors gathered a large dataset with professional annotations of translations that, according to 10 previous proposed methods, are likely to be hallucinations. This data, hallucinations along with the model that generated them, made it possible to first evaluate the performance of various detection methods, and second, to work on alleviating hallucinations at test time. For the latter, the idea is detect, then rewrite. After flagging a translation as likely to be pathological, generate several alternative hypotheses and pick the best one, relying on some measure. So far, the best realization of this general framework uses sequence probability. For detection, Monte Carlo dropout to generate several alternative translation hypotheses, and Comet QE to pick the final candidate. In this work, we use the same testbed and substantially improve the previous results. Regarding hallucination detection, we view the observation that sequence log prob outperforms previous specifically targeted to hallucinations methods as follows. Internal model characteristics may contain much more information than we expect. Therefore, Before developing or using external models and measures, we ask how far can we go if we use nothing but the translation model itself. Okay. We propose to use a method that evaluates the percentage of the source contribution to a generated translation. Intuitively, since hallucinations are translations that are detached from the source, low source contribution should be able to identify hallucinations, despite the fact that understanding hallucinations was one of the motivations behind the first method, evaluating relative source and target contributions. Both existing methods only looked at highly artificial hallucinations. We propose to use Alti plus, which we just saw in the previous paper, by the method that aggregates layer-wise tokens attributions for both hallucination detection and re-ranking in the detect and rewrite framework. For detection of the most severe hallucinations, it is twice more accurate than sequence log probability. For re-ranking, it performs on par with the previous best Comet QE. All in all, we show that we can improve the overall pipeline results by solely relying on internal model characteristics. When allowing external tools, previous work mostly focused on different ways to automatically evaluate the quality of a translation example. When allowing external tools, previous work mostly focused on different ways to automatically evaluate the quality of a translation example, either with string-based methods or neural quality estimation systems. This idea, the better we estimate translation quality, the better we are at detecting, is natural. Hallucinations are low-quality translations in the first place. However, implementing this idea in practice is challenging. Even state-of-the-art quality estimation system substantially fails. We hypothesize that instead of targeting quality evaluation, it might be beneficial to use models trained with a rather different objective. Indeed, as we show, similarity between the source and the translation estimated via cross-lingual sentence embeddings outperforms the best internal method. Interesting. So that's like laser or whatnot, or LabC. Apart from cross-lingual sentence similarity, which is expected to be sensitive to highly incorrect translations, we find the cross-lingual natural language inference model, less anticipated in the context of machine translation, also performed quite well. To the best of our knowledge, we're the first to apply these models for hallucination detection. Overall, we showed that by using only the model's inner workings, we detect the most severe type of hallucinations with twice better precision. We overwrite hallucinations at test time with results on par with the best previous method that relies on an external model. And two, models focused on semantic similarity of sentences can detect all types of hallucinations with 80% better precision than the previous methods. Interesting. So again, that's going to be a laser and LabC. Background aesthetic. We describe the framework and data we use proposed by this work. Annotated translations along with the model that produced them. What do they mean by annotated translation? What type of annotation? To the best of our knowledge, this is the only relates data that can be used to analyze the hallucinations in a clean setting. Model from Versec, trained on WMT, excluding paracroll, 5.8 million sentences, used randomly chosen 1/3 of the dataset as a held out for analysis. The model was trained on the remaining 2/3. We use the model released by this work. This is the model that generated hallucinations we analyze. Hallucination dataset released by this work contains fine-grained manual annotations of 3,415 German to English translations generated by the model above. These translations are chosen from a set of 1.8 million translations of held-out data as the ones that are likely to be pathological. The criteria used to flag the translations include 10 methods ranging from previously proposed heuristics to quality estimation models and uncertainty detectors. The taxonomy of translation pathologies in the dataset is shown in Figure 1. Here, hallucinations are defined as severe translation errors that are detached from the source. These can either be oscillatory or largely fluent. The latter is also split by severity of an error into fully detached and strongly but not fully detached. Other than hallucinations, the annotated data also contains translation errors that are deemed to be not detached from the source. See Figure 1. Overall, 323 examples are judged to be hallucinations, 1,044 as less severe translation errors, and the rest are correct. Note that so far there is no canonical hallucination taxonomy, and previous work used various, mostly overlapping definitions. We followed the taxonomy of this work for two reasons. Firstly, for consistency with the dataset and the evaluation framework we use. Secondly, this taxonomy is rather general, considers some hallucination types overlooked in previous work, strongly detached, and was shown to be reasonable. Under these definitions, properties of hallucinations differ from those of translation errors. Here are some methods that previous work has used. Generally, methods for handling can be either internal, using all information coming from the translation model itself, or external, using auxiliary models. In addition to these, we also consider oracles, relying on reference translation. Note that these cannot be used in preventative settings where reference is not available. Here we use them only for analysis. Reference-based oracles. Following previous work, they compute this character n-gram f-score of the translation with respect to reference. We use the CHRF++ that also takes into account word unigrams and bigrams. Okay, so these are just like lexical metric, pure lexical metric, and this is a neural metric, comment, which was shown to be the state-of-the-art reference-based method. Okay. Baselines. Sequence log probability. This is a standard length normalized sequence log probability. Compared to previously introduced methods specifically targeting hallucinations, this simple metric performs the best. I'm curious how exactly do they use it? Like, is it when it's low probability that they classify it as a hallucination, or what? Or just some pattern? Because, yeah. Because, like, I guess greedy can fall into oscillatory hallucinations, even though greedy is always picking the highest probability sentence, or even better, like beam search. By definition, you're seeking for a set of n candidates that are the most likely. We use Alti, percentage of source contribution. As we already mentioned above, we hypothesize that the percentage of source impact on a generated translation might be a strong signal for identifying hallucinations. To evaluate this relative source contribution, we use recently introduced Alti+. At a high level, it decomposes each transformer block into a sum of functions of individual tokens and views an output representation as a summation of transformed input vectors. Then it evaluates contribution of these vectors to the resulting sum. Among other interesting observations, Alti+ was used to show that for artificially created hallucinations, source influence is much lower than for healthy, correct translations. Our work is the first to test this intuition in a real setting where hallucinations are generated naturally. Formally, for a model and its generated translation, we compute the total source contribution as the sum of contributions of all source tokens. We do it for each target token individually and then average across target tokens. Okay. The scores are computed by the same model that produced the translations. Okay. So it's like average contribution of the source. And then external models come at QE. and they also use sentence similarity. Overall, we consider 3 measures based on pre-trained models that evaluate semantic similarity. Laser, cosine similarity of source and translation sentence embeddings from laser 2, improves the encoder-decoder from laser 1 by replacing LSTM with a transformer using teacher-student training. So we've seen this. This is something that's used in NLLB project as well for a certain set of languages. And then there's laser 3 for the students. Lab C, cosine similarity of source and translation from Lab C. Lab C is a dual encoder approach based on pre-trained transformers and fine-tuned for translation ranking with an additive margin softmax loss. XNLI, product of the entailment probabilities of source to translation and translation to source. We compute entailment scores with Roberta, fine-tuned on the combination of NLI data in 15 languages. So product of the entailment probabilities of source to translation and translation to source. Why would that help you understand stuff? I know about laser and lab C, what's intuition? If the 2 sentences lie in the same part of the space, that means they're similar in semantics, and thus they are probably not hallucinations. But what's the thing for XNLI? Anybody has an idea? Product of the entailment probabilities of source to translation and translation to source. Okay, let's continue. Main results. Overall results are shown in table 1. We report region area under curve, precision at 90% recall. We show let's see, this is different from the previous work who compare recall at thresholds cutting off a specific percentage of the dataset. Instead, we rely on 2 metrics, ROC, area under curve, okay. We show metrics for all hallucinations and fully detached hallucinations separately because the latter are the most disastrous translation mistakes that are potentially the easiest to detect. First, let us look at internal methods. We see that while Alti performs comparably to sequence for logprob, for fully detached hallucinations, it has twice better precision than sequence to logprob. So let's see logprob and Alti. So twice the precision here for fully detached, and for all hallucinations, they perform similarly. A possible root of this discrepancy is that Alti leverages the source contribution over all generated tokens. Therefore, it is more efficient for detecting translations where all or most of the generated tokens are hallucinated. Note that for fully detached hallucinations, internal Alti performs almost on par with the best external methods. 67, very comparable to the other ones here. Among external methods, LabC and XNLI substantially outperform previous best detector for both all and fully detached. Their precision and 90% recall is roughly twice better than that of sequence logprob. While such a good performance might be expected for LabC that evaluates cross-lingual sentence similarity in a way this might be seen as a measure of translation quality, results for XL and XNLI are rather surprising. To the best of our knowledge, models optimized for XNLI have not been used in the context of machine translation. This suggests that looking at a broader class of models and training objectives might be beneficial. So it's still much worse than LabC here. But yeah, not intuitive why that works at all. Note also the large difference between LabC and laser. While the former shows big improvements compared to sec log probability, the latter noticeably lags behind. Interesting. This is not surprising when looking at training objectives of the underlying models. In laser 2, the cross-lingual part of the objective uses cosine similarity between sentence encodings. Differently, LabC is trained as a translation ranking task and thus encourages ordering of translations by severity of an error more explicitly. To further understand differences between the detectors, we'll look at the distributions of the detection scores in the section 4.2 and the detected pathology types in section 4.3. Okay guys, I'll have to run very soon. I have 5 more minutes. Let me just see. Let's continue here. So then I guess why just not use LabC? What's the advantage of ever using Alti compared to LabC? I guess potentially when LabC might not support all of the languages that you care about evaluating. I mean, testing for hallucination when I say evaluating. Okay. For each of the methods, by the way, guys, for those of you who are new here, check out the channel here on my server, Open NLLB channel, for a lot of insightful conversations related to this project. By the way, we got some cool graph. Nice. Nice, that's what I was looking for. Density, number of tokens per utterance. Nice. Okay. Okay, guys, I actually have to wrap up, and then after the call, I'm gonna continue the stream. There is only a bit more, a couple pages left, 3 pages left, or 4 pages left. We're gonna wrap it up after I have done this call. Cool, guys. Catch you later. As I said, this one is a bit shorter, but we'll continue later. And yeah, cheers, guys.